Today we'll be looking at a review of function notation. First, let's talk about independent versus dependent variables. Independent variables can stand alone. They do not depend on the value of another part of the function. Dependent variables depend on the value of the independent variable in the function. So, for instance, if I have time and grades, which one is more likely to depend on the other? Well, it would probably make sense that my grade would depend on how much time I spent. So on our graph, time would come down here on the x-axis. It would be my independent variable. Grade would come up here on my y-axis. It would be my dependent variable. So as time progresses, my grade should get better. Now, we can also think of this as reported grades, like in your grade book. If time progresses, your grade could go down. Now, what we know in grade book is it tends to fluctuate a little bit, so you may end up with ordered pairs rather than a linear line. So you might end up with a, let's see if I can do that, solution there and a solution there and a solution there, and then your grade came up and then it went back down and it came up and then it came back up, and you finished the end of the semester well. A relation. A relation is a set of ordered pairs. So I could have a set of ordered pairs like, oh, where'd my pen go? I could have a set of ordered pairs like 3, 6, 2, 7, 3, 1. Those are all ordered pairs, so they would qualify as a relation. A function is an input-output relationship in which an input value x has one and only one output value y. The x values do not repeat. So our big question here would be, is this relation also a function? Well, the answer to that question would be no. It's not also a function, because we can see very clearly that our x has been used more than one time trying to repeat to different y values. Now, another way I tend to think of this is as if x represents an individual. So that's a person, and y represents a location. Now, if x is a person and y is a location, then each person can only be at one location at any given moment in time. 3 could be at the 6 party, but 3 cannot be at the 6 party and at the 1 party at the exact same time. So, as we talk about functions, this would not be a function. Domain, set of all possible x values. So, in the relationship 3, 4, 5, 6, 7, 8, 7, 9, what is the domain? Well, that's all of our x values. So we would state that it's 3, 5, 7, and we have another 7. Well, 7 and 7 are still 7. So I don't need to list 7 more than once. So our domain is 3, 5, and 7. Range. Range is the set of all possible values for the y. So in the following example, 3, 4, 5, 6, 7, 8, 7, 9. What is the range? Each of our possible y values. 4, 6, 8, and 9. Now note, these numbers are in order from least to greatest, and there are no repeating values. That's how we state our domain and range. Continuous versus discrete functions. Continuous functions include domains of all real numbers or an interval of values. Discrete functions are functions with a limited domain. when we think of continuous and discrete functions, continuous kind of gives you the indication that something goes on and on forever. So if I have a graph, an example of a continuous function would be a straight line. It's a function, straight line. No x will ever have a repeating y value. It will go on and on and on forever. Another example would be a quadratic. No x will have a repeating y value. It will go on and on and on forever. Now, discrete functions. Discrete functions are not continuous. And it sounds like a bad way of saying things because we just identified continuous function. But they are ordered pairs. So something like a scatter plot would be a good example of a discrete function, so long as the scatter plot doesn't have any x's that are repeated y's that disqualify it from being a function. So, party time, Friday at 7 p.m. Is this example an example of a function? Oh, but Mr. Gable, it can't be a function. We have more than one person going to the same party. Well, is it possible that Caleb and Katie could go to the same party? Sure it is. This is not an instance of a repeating x value, but rather this is an instance of a repeating y value. And so when we have a repeating y value, it is sufficient. It will not fail our qualifications for a function, as long as each x value is going to a different y value. Well, how about this one? Well, Zach is going to his own party. Briar is going to her own party. Daisy. Wait a minute. Daisy seems to think that she is going to be at Hannah's party and at Eddie's party at the exact same time. It's not going to be possible for for Daisy to show up to both Hannah and Eddie's party at the same time. So this would not be a function. What about this? Is this a function? Well, it's definitely a relation. We got a list of ordered pairs, but is it a function? Well, I have an x of 1. Wait a minute. I have another x of 1. So if I graphed 1 up 1, 2, 3, that's going to end up there. And if I graph 1 up 3, 4, 5, that's going to end up there. We have more than one x trying to go to more than one location. That's not going to work, and so this would not be a function. In a function, every x, the guest, has a specific y host. You can't go to two parties at once, and neither can x. We use the vertical line test as our quick way to observe whether or not something is a function. So, if the vertical line can go through the graph in more than one place, it's not a function. If the vertical line intersects the graph at only one location, then the relationship is a function. So, function or not, would this be a function? Well, we can see that we have one intersecting point on this graph, and so it passes the vertical line test, and as such, this relation is a function. The vertical line intersects the graph at only one point. Well, how about this one? Oh, fail. We see that the line intersects the graph at 3 locations. And as such, this relation is not a function. The vertical line intersects the graph at more than one point. What about these graphs? Well, on the left, we have a vertical line, and the vertical line is going to have multiple x values that repeat or try to go to more than one party. So naturally, that one will be a fail. On the right, well, we have a horizontal line. And the horizontal line only has one intersecting point when we use our vertical line test. And so this relation is a function. Function notation, f of x, is a fancy way to write y. So if I have the equation y equals 2x, we can make it a function notation very fast and very quick. We simply replace y with f of x. Whew. Slow down, Mr. Gable. That took a lot of work. No, all we did was put in f of x instead of writing in y. And we have now transformed that equation from standard y equals mx plus b slope intercept form to function notation that, notice, still looks a lot like slope intercept form. We're not changing anything on the right side of the equation. We're simply substituting then an f of x for our y value. So given an x value means that you substitute in this value into every x. If you're given an f of x value, it will mean that you substitute this value in for every y. So if we're given an x value, it would be something like x equals 4. Well, we would come up into our graph here and we would place the x with 4. So f of x equals 2x is the same thing of saying f of 4 is equal to 2 times 4. Well, 2 times 4 is 8, so f of 4 is equal to 8. If we're given an f of x value, so something like f of x is equal to 4, and then we can do the same thing. We have our f of x is equal to 2x, but we're substituting in our f of x for 4. And now all of a sudden we know that x is equal to 2. Let's try that again. Find f of x when x is equal to 4. So we want an f of 4 because we're plugging an 4 value in for every x. And that was our first x is equal to 3 times 4 minus 5. Well, 3 times 4 is 12 minus 5. 12 minus 5 is 7. So f of 4 is equal to 7. Find f of x when x is equal to 3 in the function f of x equals 2 to the x minus 3. So we're given an x value of 3, so we want f of 3 is equal to 2 raised to the 3 minus 3, which simplifies to 2 to the 0th power, and anything to the 0th power we should recall is 1. So f of 3 is equal to 1. All right, find x when f of x is equal to 4. So now we're saying this whole value is equal to 4. Now remember that f of x is a fancy way of saying y, so we could just as easily, say y is equal to 4 and plug that into the equation, y equals 3x minus 5, and lo and behold, we're substituting in there. But I need you to be comfortable using the function notation because we're going to be using it a good bit over the next week and a half. So f of x, this value, 4, is equal to f of x. And now we can solve the rest of the equation just like we would normally. Add 5 to both sides. 9 is equal to 3x. Divide by 3. And x is equal to 3. All right, we can do the same thing in our next equation. F of x is equal to 8. So we're going to take the 8 and we're going to plug it into our notation. 8 is equal to 2 to the x minus 3. Now, it has been a while since we have done a problem like this. In order to be able to solve this, we need to have like bases. Well, is there any base 2 that when we multiply it by itself is going to give us 8? Well, let's think. 2 times 2 is 4 times 2 is 8. Whoa. So 2 to the 1, 2, 3 power is equal to 2 to the x minus 3. Now, back at the beginning of the year, we said that if we have the same base, we can set our powers equal to each other. So 3 is equal to x minus 3. We add 3 to both sides. 6 is equal to x. Now, this one takes a little bit for us to remember, which is why we just did a few basic examples with it at the beginning of the year. We're going to continue to do more examples with it at the beginning of the year, but it all comes down to being able to break that number down into an exponential statement. Application. What is the domain? Well, the domain is all of our possible x values. So we need to look at our chart up here and figure which ones are independent, which ones are dependent. Well, the amount that I can travel depends on the amount of time that's passed, so x and y. Now, we know our independent variable, which is our x. We can list our domain. 1, 2, 3, 4, 5, and 6. All right, what is the range? Well, the range is going to be all of our possible y values. 4, 8, 12, 16, 20, 24. What is the function that represents the data? Now, before I get to function, I would probably start with what is the equation that represents the data, because it's going to be a little bit easier to do that. And we should see pretty clearly that these are increasing by values of 1. These are increasing by values of 4. So we have a constant rate of change of 4. Constant rate of change is our slope. So y is equal to 4x. Now we need to find our intercept. Well, if these are decreasing by 4 each time, and these are increasing by 1, we should be able to come down to 0, which is nice because that's an intercept. Hey, wait, that's also 0. So our slope-intercept form equation is y equals 4x, but it didn't ask for slope-intercept form. It asked for the function. We're going to state the function in function notation, which means we replace the y with the fancy version of y, f of x. What is x when f of x is equal to 4? Right, this is one of those options where we're taking this f of x value and we are substituting it with 4. So over here, f of x is getting replaced with 4 equals 4x. We divide both sides by by 4, and x is equal to 1. What is f of 2? So f of 2 in the equation f of x equals 4 is equal to 4 times, we're replacing x with 2. 4 times 2 is 8. So f of 2 is equal to 8. Operations with these functions. Find f of x. Use f of x equals 3x plus 5 and g of x equals 5x. So we want to find f of x plus g of x. Well, f of x is this value, so we're going to substitute that in, 3x minus 5, and we're going to add to that g of x, which is this value, and so we're going to substitute that in, 5x. Now, since I have addition signs or positive values in front of both parentheses, I no longer need the parentheses. 3x minus 5 plus 5x. 5x and 3x gives me 8x minus 5. So f of x plus g of x is equal to 8x minus 5. Find f of x minus g of x. Well, that's going to be very similar. Our f of x value is still 3x minus 5, minus our g of x value is still 5x, but this time we need to pay very close attention to the fact there's a negative sign in front of that, so it's going to distribute a negative 1 back into the parentheses. So we end up with 3x minus 5. Negative 1 times 5x is negative 5x. Again, we will combine our like terms. 3x and negative 5x gives me a negative 2x minus 5. So f of x minus g of x is equal to negative 2x minus 5. Find f of x times g of x. So again, same process. We're going to substitute in our f of x, which is 3x minus 5. And we're going to multiply it by our g of x, which is 5x. And we have a monomial times a binomial. If you need to reverse the order, you may certainly do so, because that makes it far clearer to many of you that we're distributing. And we distribute to both terms. 5x times 3x, so 5 times 3 is 15. X times x is x squared. Minus 5 times 5 is 25x. Find g of x minus f of x. So g of x is 5x minus f of x is 3x minus 5. And so again, we want to pay attention to in front of the parentheses. We see that there's a negative sign, so I'm going to put a 1 there and distribute that value back into both terms inside the parentheses. So let's carry down our 5x. Negative 1 times 3x is negative 3x. Negative 1 times negative 5 is positive 5. Combine your like terms, and we are done with the problem. You try these following too. All right, welcome back. We have b of x, which is equal to 2, times r of x, which is equal to 11x, plus w of x, which is equal to 4 minus 5x. So we will do our order of operations, multiplying first. 11x times 2 is 22x plus 4 minus 5x. Order of operations, we're going to combine like terms. 22 minus 5 is 17x plus 4. Number 6. W of x is 4 minus 5x minus, and we have a bracket, so I'm going to go ahead and use the bracket until I figure out what's getting simplified here. R of x is 11x plus b of x. Well, b of x is 2. So what in the world are the brackets doing? The brackets were only here because our x in our function notation had parentheses already, and so it looks very odd to have parenthesis followed by a parenthesis. And so we get into using brackets. Well, now I don't have any parentheses anymore, so if they're confusing you, you can get rid of them. Otherwise, they function like parentheses. So we can rewrite this 4 minus 5x minus 11x plus 2, and now we just see it's parentheses. Either way, we need to look back and front to see, is there a negative value? Yes, there is. So we're going to add our 1 and distribute it back into every term inside. So negative 1 times 11x is negative 11x. Negative 1 times 2 is minus 2. And the rest of the problem drops down, 4 minus 5x. At this point, we'll combine our like terms. Negative 5x, negative 11x gives me negative 16x. 4 and negative 2 gives me a, what are you doing? All right, I've lost the ability to write. I'm not sure what it's doing. Gives me a plus 2. So we would have negative 16x plus 2.